We'll have our last talk of today, and this will be presented by Henry Sinclair-Banks, and he will be talking to us about acyclic Petri nets, workflow nets with resets.
Thank you very much, Prakash. Right, yeah. Hello, my name is Henry. I'm a PhD from the University of Warwick, and indeed today I'm going to be talking about acyclic Petri nets and workflow nets with resets added. This is joint work with my supervisor, Dmitry Justikov, and also Wojciech Czerwiński, Piotr Kaufman, and Filip Mazowiecki. And don't worry if you're new. I get the impression that some people are not so familiar with VAS or Petri nets. I'll kind of give a definition, but it will be fairly light touch for those that do know. So yeah, without further ado, what's a Petri net? So we've already heard in Chris's talk that Petri nets are equivalent to VAS, but they look rather different. This is a Petri net. Here's an example. So Petri nets have places and transitions that can move tokens. You've got a non-negative number of tokens in each place. Here I've got 4 tokens in P1, 5 tokens in P2, and then in Q, R1, and R2, I've got 0 tokens. And transitions can move them around in the way that you would expect. So if I was to fire T1 here, I would consume 1 token from P1, 1 token from P2, and then I'd put 3 into Q, like this. And then now I have the ability to fire T2 because I've got 3 tokens in Q. I can take 1 to consume. I can put 5 in R1 and 1 in R2. Okay, fine. And this is equivalent to VAS. I won't explain why. If you want, I can explain separately afterwards. That's fine. I'll introduce a little bit of notation that's like slightly different. So a marking is just a configuration. It just tells you how many tokens are in each place. In this, I've got 3 in P1, 4 in P2, 2 in Q, 5 in R1, and 1 in R2. And a run is the same kind of thing for VAS. It's just a firing sequence of transitions. You've seen one already. I've just shown you a very short 2-transition run where I started with the marking 4, 5, 0, 0, 0, and I went to this marking here by first firing T1 and then firing T2. And you've already seen now twice, now for the 3rd time, some decision problems for these models. So I'm going to have 2 decision problems that happen to be reachability and coverability. Who would have guessed? They take input, a Petri net in this case, an initial marking I'm going to call U, and a target marking I'm going to call V. Reachability says I would like to go from U exactly to V, and coverability says I'd like to go from U to some marking that is at least the target. So I'm allowed more tokens in each place than necessary. Workflow nets is something else we study. So in workflow nets, they have some special features. This is not a workflow net, and I'll explain why in just a moment. In a workflow net, you have some designated initial place, we'll call it I, and some designated final place, which will denote F. I cannot be produced to, so it can only really be consumed from, and F has the opposite, that it can be produced to, but cannot be consumed from. And every place and every transition is on some path from the initial to the final. Now, this is not a workflow net, firstly, because I've not given you the initial or final place, but also even if I did, let's say P1 is the initial and R1 is the final, then P2 is not on a path between the initial and the final. So I need to change this. I'll add an initial place, and I'll add this transition to produce some tokens to P1 and P2, and I'll add a final place. And now I'll notice that every transition and every place is on some path from the initial to the final. And so, yeah, this indeed satisfies the properties that one needs for a workflow net. Surprisingly, but not surprisingly, if you think about it for a short while, the complexities of reachability and coverability coincide for Petri nets and workflow nets. So we've already heard from Łukasz that reachability is Ackermann-complete and coverability is FSPACE-complete. These are, like, to answer the question from the gentleman in the pink shirt earlier, very difficult problems, and they remain difficult even with the restriction of workflow nets. Very roughly speaking, you do roughly what I did here. You take any old Petri net, you add a new initial place, you add a transition like T0 that sort of spawns the initial marking, you add a new final place F, and some like final transition, in this case T3, that kind of consumes the target marking. You have to do a little bit more because you kind of need to make sure that every place and every transition is on some path, but you can add some extra places and transitions to make this work out. But I won't explain anymore. So I'll move on to Petri nets with resets. This is a more powerful model. So when I add resets, I'll denote this with this red dashed edge. So in this case, transition T2, when fired, resets P1 and R2. What does that mean? So the semantics are as follows. First, a transition consumes, then it will reset, and then it will produce. So to have a look, what happens when you fire T2 from this marking? First, you consume 1 token from Q, then you'll just empty P1 and R2 to reset them, and then you'll do the production. So I had to expand R1 a little bit to shove 10 tokens in there, and I'll have 1 token back to R2. this problem's really, really hard, right? Like we've jumped up from Ackermann to undecidable, unfortunately, and coverability jumps up from XSpace to Ackermann. And so these problems are like seriously difficult. And so if you wanted to do any form of verification, you're probably going to struggle. And like, why resets? Like, why would you want resets? In some systems, either by design or by accident, you might end up in some configuration that's kind of bad in some sense or not useful. You might want to literally restart a process. It's very natural. And you can't do that in a VAS or a Petri net because you don't have zero tests. You can't kind of come back, test for zero, and then continue. So maybe you just have a button that does reset, and resets indeed model this nicely. But unfortunately, the complexity really jumps. So something's got to give. We add acyclicity, so we restrict the model after extending it, hoping to get some reasonable tractable decision problems. So the semantics don't change. It's just the structure of the Petri net that we consider. That's the only thing that changes. Actually, this thing is acyclic. So in our definition of acyclicity, you just look at the graph consisting of the places and the transitions connected by these consumption and production arcs. We do not count the reset edges. In a sense, it's hard to say which direction they follow. We'll call the productions arcs and the consumptions arcs, but we'll call the resets edges. There's sort of no directionality. It does look like you have a cycle P1, T1, Q, T2 back to P1, but this uses a reset edge, which doesn't count. And so, yeah, this example the whole time, surprisingly, has been an acyclic Petri net with resets. And yeah, this talk is about like what we study. So we study acyclic Petri nets with resets and acyclic workflow nets with resets. And just to give a mention that acyclicity really restricts your model without resets. So if you were just to restrict Petri nets and workflow nets to be acyclic, then reachability and coverability are all NP complete in all the four combinations where you combine reachability and coverability in Petri and workflow nets respectively. So this really restricts the what you can do. So let's talk about like what we've done when we have both the extension with resets and the restriction with acyclicity. So indeed, we study acyclic workflow nets and acyclic Petri nets with the resets, and we indeed study coverability and reachability. So the first theorem that we have is that if you consider workflow nets and the reachability problem, then you're in PSPACE. This is a massive improvement over what we had before, which was undecidability, but is somehow harder than NP. And this is what one would expect because we have resets. These are quite powerful. And theorem 2 says that if you consider coverability and instead Petri nets, then you remain inside PSPACE for somewhat similar reasons. And theorem 3 is that actually these problems are pretty tough already. So if you have coverability and the workflow restrictions, then the problems are PSPACE hard. And so we can do a bit of jiggery-pokery and notice that this lower bound extends both ways, right? The reachability problem is harder than coverability, so this lower bound will extend. And well, workflow nets is just a strict restriction of Petri nets, so of course this lower bound will extend downwards. And so we know that coverability in acyclic Petri nets with resets is PSPACE complete, and reachability in acyclic workflow nets with resets is PSPACE complete. And the same true in the other direction. So these upper bounds come back for acyclic workflow nets for the coverability problem. And so this problem too is PSPACE complete. So far, so good. But unfortunately, with acyclicity, undecidability persists, which I think is rather surprising. And this is the first kind of obvious occurrence when the complexity of reachability differs in workflow nets and Petri nets. We saw without resets and without acyclicity, both problems were Ackermann complete. With just resets, it became undecidable in both models. And with just acyclicity, both were in NP, but now we have a difference, PSPACE to undecidability, which is kind of odd. And I should note, this is important, but will not be focused on in this presentation, that these results hold regardless of the encoding. And when I say encoding, I'm talking about the encoding of the arcs themselves, like how many tokens you're consuming or producing to certain places. If you encode this in unary or binary, PSPACE holds either way. Okay. So I'll share some of the ideas that we used to get here. So the first is for theorem 1, which is acyclic workflow nets with resets. The reachability problem is in PSPACE. So, okay, let's suppose reachability holds. Indeed, there'll be some initial marking. We'll suppose this is at this one is like putting one token in the initial place, and we're aiming for reachability where we have one in the final place at the very end. We're going to ignore resets for a moment in the run. I'll explain why in just a moment. And we're going to consider the number of times each transition is fired. Like, why ignore resets? Well, if you just pretend to remove resets from your model, well, then the markings that you see after firing a transition are only going to be bigger because resets only decrease the number of tokens that are available. So if you ignore them, you see bigger markings. I'm going to argue that even once resets are ignored, the markings you see are not so big. And we're going to use the following fact, which is that workflow nets have the property that all transitions must consume a token. Like, why is this the case? Suppose that's not true. Suppose there's a transition that doesn't consume anything. Well, if it doesn't consume anything, then there's no incoming arc. But I said that a workflow net must have every transition has a path, is on a path from the initial to the final. As if there's no incoming arc, then certainly it can't be on a path from the initial to the final. So indeed, we must be consuming something. And so from the very initial place, there will be a transition that consumes a token, right? Like, this has to happen. And suppose it produces m many tokens. It doesn't matter exactly what m is, but suppose m is the maximum number of tokens any transition produces. So firing this will shove m tokens to this next place. And well, T1 can only be fired once. That's pretty obvious. And now suppose T2 does the same thing. It consumes just one token because it needs to consume at least one token. And suppose it too produces the maximum number of tokens. This could be fired m many times, right? Because we would have produced m many tokens to that place. You can see this argument repeating, right? And by the nth transition, we'll be able to fire this at most m to the power of n minus 1 many times, right? If you imagine this all stacked up. And if I suppose there were n many transitions, then we have a bound on the maximum number of tokens that were possible to put in a place. This is m to the n. And remember, this is just without resets. If there were resets, this number might be even smaller. So this really is a global bound on the maximum number of tokens you could physically put in a place in a workflow net. And well, this marking can be represented using polynomial many bits. So if you write down a marking in binary, then this will have log of m to the n amount of space required. If you kind of see this out, this is m times log m. N is the number of transitions, is clearly bounded above by the size of the machine, and log m is clearly bounded above by the size of the machine because it's the maximum number that you ever see on top of a production transition, production arc, sorry. And so this is a polynomial value. And how do we get the PSPACE algorithm out of this? Like, what's the kicker? Well, if I can write down any reachable marking using polynomial space, then I just use a non-deterministic polynomial space exploration algorithm over the states or over the configuration space, or rather the marking space, as I would call it. So that gives the rough idea. So the next idea is the PSPACE lower bound. This is a bit harder, and I think I've got time to explain through some of it. So we'll see how it goes. So we say that coverability, so not reachability as we saw in the previous slide, is PSPACE hard. So we're going to reduce directly from the quantified satisfiability problem. So let's suppose we're given some quantified satisfiability formula. So the flavor that we care about is when we have universally quantified, then existentially quantified single variables nested n many times. I'm going to, for sake of clarity, I hope it's okay, represent universally quantified variables with y and existentially quantified variables with x. And so we care about this statement here. For all y1, there exists an x1. For all y2, there exists an x2, etc., such that phi holds. Okay. And we're going to construct a net. Here's the sketch. I will show an example, and I'll try and talk through it. So we're going to have some places. These are really representing gadgets. This is not like true to the form, that represent like each quantified variable. And they'll be in some way consumed from and produced to places corresponding to each literal. So if we would like to, if we have, there exists x1, then we'll be able to choose whether we put a token in x1 or x1 bar. And for universally quantified, we'd like to iterate through. So first we'll put a token in, I've made a typo here. These should be y's and x's mixed. But you get the idea that if you have a universally quantified variable, then you would like to copy down a token to first x2 and then x2 bar to go through all the combinations of the universally quantified variables. And then these will be kind of pushed to all the clauses for which those literals belong to in some way. And then finally, we'll have this like special satisfaction transition, which will try and gobble a token from each place. And if you have a token in a clause place, this will be representing that a clause is satisfied. So you'd like to be able to collect tokens from all of them, saying like, oh, all clauses are satisfied, which is what you would like for QSAT. And then we'll put one token in this final place F, right? Remembering this is a workflow net. And the number of tokens in F will count the number of times we satisfy. And we'd like to be able to put 2 to the power of the number of universally quantified variables, many tokens in F, right? That's like how many times you have to check QSAT. Okay, so maybe a bit more detail on how this works. Here's a horrendous example that I made earlier. It's not as bad as it looks. I'll talk you through it very briefly, but I kind of just wanted to show you that firstly, this isn't very easy, and also that it is real. Like there's the reason I gave you a sketch first. We'll have an initial place all the way at the top left and a final place all the way at the bottom right. If you kind of look, if you look here, first, you'll be producing tokens to not y1. This is a universally quantified variable. And then there'll be a token sat in this place. And then later, you'll be firing a transition into y1. So at some point, there'll be tokens here. And at another point, there'll be tokens here. However, for existentially quantified variables, you get the choice when there's a token here, whether to fire this transition or this transition. So for universally quantified variables, you're really forced to sequence, setting it to false, then true. Whereas for existential variables, you get to choose whether it's false or true. And this kind of nests itself in some crazy way. These values here are to sort of keep the number of tokens in memory, so to say. So we'll produce more tokens for like outermost quantified variables and less tokens for innermost quantified variables. And note, like, I thought this was about resets. Like, I haven't drawn the resets because it would be an absolute headache if I did. Pretty much every transition resets every single place below it and to the right, which would make a lovely dotted red mess if I were to do so. So then once you have these loaded up with some tokens, you'll then have these transitions that will fire into the clauses. So C1, C2, C3, and C4 correspond to these 3 clauses. Just to look at C1, for example, you'll be pulling a token from the Y1 place. You'll also be pulling a token from the typoed X1 place, and you'll be pulling a token from the not Y2 place. And there's these extra 6 places that correspond to like dummy clauses that are just Y1 or not Y1, X1 or not X1. They're there just to force you to fire every transition through. And then eventually you'll have a satisfaction transition that will gobble tokens from every place, reset them all, and put 1 in F to say like, yep, we survived this iteration of QSAT. I'm happy to explain in more detail for those who are interested later, but I'll leave that for now. The final idea that I'll share with you. Yes, question. I've made a mistake. It should be from the X, not the X bar. My apologies. You're right. And to share the final idea, I'll share roughly how undecidability works. So I claim that reachability with acyclicity remains undecidable. How does this work? We do it with 2 lemmas. The first, instead of dealing with resets, as we've seen in previous presentations, we're going to deal with 0 tests because they're ugly. This is a classic reduction using resets to simulate 0 tests, so I won't show it here. The second lemma is the interesting one. Like somehow we can just remove acyclicity. Like what gives? Very roughly, we're going to simulate not necessarily acyclic transitions. We're going to simulate all the transitions with some sort of transition controller. Imagine this is the Petri net, just the most simple cyclic thing I could draw that's remotely interesting. So note that there is clearly a cycle from S to R, down to T, back to Q, like I'm not going mad. So we're going to draw this thing. It's not actually as complicated as it looks. I'll talk you through it. So we're going to have these top transitions that are going to be guessed. Note that this is not a workflow net. This is a Petri net. So we're allowed transitions that are not reachable from some given initial place. So if you would like to fire S in the original, we're going to fire S prime. It's like you guess the transition that you're going to fire. This would produce 2 tokens, right? 1 to the left and 1 to the right here. This transition below the left place will simulate the consumptions. Note that it consumes from P and consumes from Q, just like S does in the original. And this transition here will simulate the productions. Look, it will put a token to R, just like S puts a token to R in the original. And note that this transition, the like production simulator, requires that this place is empty. So really, you have to fire this transition before you fire this transition, which preserves the semantics of Petri nets as one would hope for. And moreover, once you fire S prime, guessing that you're going to fire S, you'll put 2 tokens here. But notice to fire S prime or to fire T prime, you need all of these places to have 0 tokens in them. And so you can only fire them once they're all empty. So you guess S, you put 2 tokens here, you have to fire this transition first, then this transition before you can fire S prime or T prime again to continue. And this thing's always acyclic. Notice that At the very bottom, you'll have the consumption places, and there are no cycles here. Like it looks like you might, but indeed the bottom level of this acyclic Petri net are the consumption places. Then you'll have the places that are like simulating the original places, and then you'll have the production transitions themselves. This thing's acyclic because the zero tests don't form a cycle as well. And so this gives you very roughly the ability to simulate not necessarily acyclic transitions. And although I've not included it here, you could just have zero tests in the Petri net, copy them over to here, and now you're simulating just an arbitrary Petri net with zero tests. And reachability here is undecidable, so reachability with acyclicity force must also be undecidable. And so that concludes the talk. So to summarize, here are our results. We show that coverability and reachability in acyclic workflow nets with resets are both PSPACE-complete, and acyclic Petri nets with resets, the coverability problem is PSPACE-complete, but the reachability problem, surprisingly and maybe unfortunately, is undecidable. And for future work, this could be a good basis to study the soundness problem, which I won't define for sake of time here, in acyclic workflow nets with resets. And there is also the question whether reachability or coverability in acyclic affine Petri nets or workflow nets is decidable, where affine is a strengthening where you're able to multiply the number of tokens. So you can take a transition that doubles the tokens from one place to another. So this is a more powerful model, but maybe with acyclicity, this becomes like reasonable. Yeah, thank you very much. I hope you enjoyed my presentation.